Today we're going to be starting Chapter 2, which is on linear equations and functions. And Section 2.1 is on how to represent a relation and a function. So our goal is to take these relations and represent them as both functions and non-functions, and then also to graph linear functions. So a few terms we're going to talk about. First, a relation is a mapping or a pairing of input values with output values. The domain is the set of input values. The range is the set of the output values. So we're going to take a relation and we're going to represent it, and there's a bunch of different ways we can do it. So we have ordered pairs, we have this table, we have a graph, and we have a mapping diagram. These are all ways that we can represent a relation. So we're going to take these ordered pairs, and we've seen these a lot. Okay, and so this is a relation. We have 4 ordered pairs here. We could also write this in an XY table. And if we do it as an XY table, it'd be very similar. So here's our relation in table form. If we do this as a graph, we would just plot these points. So we're going to plot the point 2, 1, negative 2, 2, 0, 3, and 2, negative 1. So that's what our graph would look like, the relation in a graph. And the mapping diagram is something that you may not have seen before. Now, most of us have seen ordered pairs in the table and the graphs before, but you may not have seen this one before. We're going to have input values and we're going to have output values. And then what we're going to do is we're going to write the inputs in order from least to greatest. So we have a negative 2, we have a 0, and we have a 2. Now the 2 occurs twice. We're only going to write it once in the input-output. And we're going to do the same thing with the outputs. So we're going to go negative 1, 1, 2, 3. So now, when we talk about this, our mapping tells us, well, we know that the ordered pair is 2, 1. So 2 goes to 1. And negative 2 is 2. So negative 2 goes to 2. 0 goes to 3. And 2 goes to negative 1. So that's what a mapping diagram will look like. And most of the time you're going to see these circled like this. So that's what an ordered pair, a table, a graph, and a mapping diagram. These are all ways that we can represent relations. Now, in example 1, it says we want to consider the relation given the ordered pair 3, 2, ordered pair negative 1, 2, negative 1, negative 2, 1, and 0, 3. We want to identify the domain and the range. Well, remember, we said that the domain is the x values. So in this case, the domain, we're going to take the x values, and again, we're going to write them in order from least to greatest. So negative 2, negative 1, 0, 2, and 3. Those are the x values. The range is the y values. So that's going to be negative 1. We have a 0. We have a 1, a 2, and a 3. So there's our domain and a range. He says represent the relation using a graph and a mapping diagram. All right, so if we graph these, let's do the graph on the left side over here. So we're going to graph these ordered pairs. 3, 2, negative 1, 0, 2, negative 1, -2, 1, and 0, 3. So that's what our graph would look like of this relation. Now if we go to the mapping, again, the nice thing about having the domain and the range is we can just write these right down the line. And then we're going to draw where they go to, where each point is mapped to. So 3 is mapped to 2. -1 goes to 0. 2 goes to -1. -2 goes to 1. And 0 goes to 3. So that's what our mappings look like. So we have the mapping on the right side, the graph on the left side. So then we're going to talk about functions now. And a function is a relation for which each input has exactly one output. Okay? Make sure you know that. Each input has exactly one output. So for every input, it can be mapped to only one output. So let's look at example 2. We want to determine, are these relations functions? And then explain your reasoning. Well, -5 goes to 4, -1 goes to 0, 3 goes to -1, and 3 goes to -2. 3 goes to 2 different values. So this is not a function. Because the input 3 has more than one output. Okay, so that one is not a function. Well, if we look at the next one, -3 goes to 5, 0 goes to 5, 2 goes to 1, and 6 goes to -8. Each input has its own, or has a output value, and only one output value. -3 only goes to 1, 0 only goes to 1, 2 only goes to 1, and 6 only goes to 1. So this is a function. Because each input has only one output. Therefore, this one is, in fact, a function. So at this time, I want you to go ahead and do guided practice questions 1 and 2. They are on page 73 in your book. So go ahead and pause the video, and you can hit play when you are ready to continue. And here are the answers for the guided practice questions 1 and 2. Notice we have the domain and range for A in part A, and B we have the graph here on the left and the input-output table on the right. Then number 2, way on the far side, it says, is that one a function out of the book? And it is a function because each input has exactly one output. The next thing we're going to talk about is something called the vertical line test. And that's a relation is a function if and only if no vertical line intersects the graph of the relation in more than one point. So let's say we take a graph that looks like this. So what they're saying is, can we draw a vertical line that touches the graph in more than one place? Well, if I take this vertical line, it only touches once. It only touches my graph once. It only touches my graph once. Okay? So no matter what, I'm going to draw this, and it's only going to touch, the vertical line is only going to touch the graph once, so those are functions. If we turn this parabola on its side, Now, is there anywhere that we can draw a vertical line that touches it more than once? And the answer is yes. It crosses here, it crosses here. It touches the graph twice. My vertical line touches the graph twice, so it is not a function. So this part fails the vertical line test, therefore it is not a function. So if we look in example 3, and that's on page 74, they give you a couple graphs, and the first one is a scatter plot of points. And when you see those, if you have a scatter plot that looks like this, the question is this a function? And the answer is no, because right here we can draw a vertical line and it touches it twice. So this one is not a function. Okay, so this relation is not a function. The second one, the points go up in a trend like this. There are no vertical line. It passes the vertical line test, actually. So no matter where we draw a vertical line, it's only going to touch at one place, one dot. So this one is a function because it passes the vertical line test. Okay, so the first one was not a function because it failed the vertical line test. The second one is a function because it passes the vertical line test. All right, we're going to jump ahead to equations in two variables. And that's an equation that contains two variables. And most of the time, we're going to talk about x and y. The independent variable is the input variable, and the dependent variable is the output variable. So when we graph equations in two variables, we're going to, step 1, construct a table of values. Step 2, plot enough points so you can recognize the pattern. And step 3, connect the points with a line or a curve. So when we talk about example 4, you've graphed equations that look like this hundreds of times now. Y equals 3x minus 5. It is linear. So it's in slope-intercept form. Y equals mx plus b. You can do one of two ways. You can make the table of values like they say. Put in 0, we get negative 5. Put in 1, we get negative 2. Put in 2, we get 1. Or you can use slope-intercept form, knowing that the slope is 3, the y-intercept is negative 5. Either way, you're going to get the same result. So I'm going to use slope-intercept form. The y-intercept is down here at negative 5. The slope is 3, so I'm going to go up 1, 2, 3, and over 1, up 1, 2, 3, and over 1, up 1, 2, 3, and over 1. So here is my graph. If we'd have plotted these points, 0, negative 5, we'd have got there. 1, negative 2, we'd have got there. 2, 1, we'd have got there. So notice they are the same points. So it doesn't really matter which way you do it. Obviously, if you can do it using slope-intercept form, it will save you some time. A linear function is a function that can be written in the form y equals mx plus b, where m and b are constants. We just got done talking about that. And then function notation says using f of x, or a similar symbol such as g of x or h of x, to represent the dependent variables of a function. So when we look at y equals mx plus b, that is xy notation. And if we look at f of x equals mx plus b, that is in function notation. Notice these two are the same. They're the same thing, mx plus b. Just we have y equals, it's xy notation. If you see f of x, that means it's a function notation. And let me tell you why function notation is great. Okay? And that's because when you plug a variable in, or a value in for your variable, you will have the input and the output value. You'll know what that ordered pair is. That's not always the case in XY notation. So if we look at example 5, it says classify and evaluate functions. Tell whether the function is linear. Well, we know that this is linear. Y equals mx plus b. The reason it's linear is because we have an exponent of 1 in the numerator. Okay? That is what makes this equation linear. So if it's anything other than that, it's not going to be linear. So tell whether the function is linear in example 5a. Not linear. To the third power. It's actually a cubic, but either way, it's not linear. So now it says evaluate the function when x equals -3. So what we're going to do is we're going to plug that in. F of -3 equals -2 times, and then -3 to the third, plus 5. So you're not going to do anything with the left side. It's just f of -3. Now we evaluate the right side. -3 cubed is 27, -27. So -27 times -2 is 54. Then we have plus 5. So f of -3 equals 59. So it's not linear, and f of -3 equals 59. So again, jumping back here, we know that -3 was our input value, and 59 is our output value. Okay, so we put in -3, we get 59. So that means we have an ordered pair of -3, 59 as one of our solutions. That's what's really nice about function notation. You have the input value and you have the output value. All right, next, b. Well, this one is linear. Has an exponent of 1. It's in y equals mx plus b form. So now let's find g of -3. Again, we're just plugging it in. 8 times -3. So this is going to be 12 minus plus 24. So g of -3 is going to equal 36. Okay, and again, that is the form that you have to have your answer in. -3 is the input, 36 is the output. There is your solution. All right, so I would like you to jump to page 75. On the bottom of page 75 are guided practice questions 4, 5, and 6. So go ahead and do those 3 quickly. You can pause the video and hit play when you're ready to resume. And here are the answers for the guided practice questions 4, 5, and 6. So when we look at section 2.1, we're talking about representing relations and functions. And that's what our goal is. We want to tell, are these functions, how can we represent them, and how do we tell if they're functions? Well, we looked at a couple of different ways. The vertical line test. If we have the graph, we can tell, does it pass the vertical line test? If it passes the vertical line test, it's a function. Okay, if we just have a mapping or a pairing or anything like that, we look at the pairs. Does each input value have only one output value? If it does, then it is a function. So those are the things we are looking at in section 2.1. So here is your homework assignment. It's on page 76 for section 2.1.